Good evening, students. I'll start the class. Today we'll start with a new chapter, that is thermodynamics. Okay, thermo. This is dynamics. Thermo means related to heat, and dynamics means always the motion or the movement. Would say the flow or transfer of heat. Okay, the movement of the heat from one form to another. So in the previous chapter also we have seen what is heat. Heat is nothing but a form of energy. Which gives you the sensation. Actually, you cannot see that energy, it can only be felt, you can only feel it, the heat. Okay, it is a form of energy which can produce the sensation of warmth. We have seen what is the unit of heat in the previous chapter also. We always write it in terms of joules. So that is SI unit. Heat we always express in terms of joules. Suppose if you want to write in CGS system, then it is called as calorie. This is CGS system. Now what is this one? Suppose if I want to know what is 1 calorie. If I have water, suppose, okay, I take just any substance, consider anything. If one substance is there at suppose 27 degrees Celsius, I take 1 gram of it, just a small part. I just take 1 gram of this, okay, that I take 1 gram, and I want to raise its temperature from 27 to maybe 28 degrees Celsius. Okay, if I want to increase any substance temperature, definitely I have to provide some heat. So that how much ever heat I need to change this 1 gram substance temperature from 27 to 28, it means by 1 degree I'm making it rise. That amount of heat is given as 1 calorie. So 1 calorie, it is defined as the heat energy required to raise the temperature of 1 gram of water through 1 degree Celsius. Okay, it could be from 27 to 28 or 14 to 15 or 28 to 29, anything, but change by 1 degree Celsius, how much energy you need to change 1 gram of water. Okay, so that is called as 1 calorie. Now the relation between joules and calories, by solving in the previous problem also I had given 1 calorie is actually 4.186 joules. If you want to convert calories into joules, it is 4.186. Normally while solving problems and all, sometimes we take it as 4.2 approximately, but the actual value is 4.186. Okay, so this is about heat. The thermodynamics is also everything related to heat only. So we'll see what is thermodynamics. Thermodynamics is study of, or it's a branch that it is a branch of science that deals with heat and temperatures, and the interconversion, heat and other forms of energy. Now I told you there are various forms of energy in the previous chapter. Heat, that can be heat energy, okay, or even work. Work done is in the form of energy only, because even work has the same unit as joules. But only this is what non-mechanical, and work would be mechanical. I told you, you need some kind of external force or something to do the work. Here, heat will be in based on the molecules. The transfer directly takes place from molecules to molecules. That we'll see in detail anyway. Various forms of energy. So that is interconversion. Interconversion means heat can be converted in terms of work, and work can be converted in terms of heat. They are both form of energies only. They can be converted from one form to another. That's why it is called interconversion. And vice versa. Vice versa means ulta, back from here to here. So it is nothing but which deals with the heat, temperatures, and conversions from one form to another. Now, before starting the Excel list detail, I just want to tell you what is called as a adiabatic wall and diathermic wall. Although the terms are looks complicated, they're simple actually. First one is, I'll just tell you what is adiabatic wall. Adiabatic means, suppose if I have a box, okay, and I want to put this some adiabatic wall, it means it is some insulating system. Don't draw this, I'll give you later on. Insulating system. Now you know that what is the property of an insulator. Insulator always tries to block anything, okay, either current or any, it may be any form of energy. So what is going to happen if you are putting some hot water here and you are surrounding it by entire insulating system? What will this insulating system do? It will not allow this energy to flow from the higher temperature to the lower temperature outside. It is basically blocking it. Okay, so it is called as an insulating system. Instead of using the word insulating, they'll be using it as a adiabatic wall. It is nothing but a insulating wall. Does not allow flow of energy. Same way how it does not allow from outside, inside to outside, same way from outside to inside also it is not allowing. It's just like blocking both the ways. Then the second type of wall is diathermic wall. So it is opposite one. The amathermic wall is conducting wall. Conducts electricity and all means it is allowing it to pass. Conducting means it allows flow of energy through it. If you put a conducting wall and you put hot water, it will pass through it to the outside, or whatever is outside can come inside. So that is called as a diathermic wall. It allows flow of energy. Then there's something called as, you may come across the word macroscopic. Or properties of a substance. What are these macroscopic variables called? They are nothing but pressure, these terms, pressure, temperature. These are just the examples I'm giving. Volume, which can be like externally measured. Okay, you can always measure this. Macroscopic means at a large quantity, bigger area wise. Whichever you can from outside, you can always calculate. Whereas microscopic would be like at a very minute level, like consider molecules, atoms, which we cannot see. Okay, they are at a very microscopic level. But macroscopic, these are the ones: pressure, temperature, volume, mass. So the word, if you come across when they are mentioning, when the macroscopic variables do not change, sometimes they say What they are trying to say is maybe the pressure, temperature, volume, mass of that substance is not changing. Next, I try to what is the thermodynamic equilibrium? Okay, don't write what I'm explaining as of now. Suppose if you have a hot cup of tea and you keep it outside, okay, it is suppose at 80 degrees Celsius, and then this temperature it has a is at a lower one. Okay. Now what is going to happen? Obviously, if it is open, left open without any insulating wall, slowly the heat will get transferred outside, and then it will make sure that it comes to the room temperature. Means at some point maybe it turns out to be, if room temperature is outside 27 degrees, it will make sure this is also at 27 degrees Celsius. So till then, till it comes to room temperature, all the energy will start flowing out. Now this is called as thermal equilibrium. Okay, and still your temperatures become equal compared with the surrounding. The heat energy will always go from higher to the lower. If you put ice here and there outside it is hot, then heat energy will come here and try to melt the ice and then bring the water to the room temperature with some time. The process works in trying to maintain a balance with the surrounding environment. So balancing the temperature is called as equilibrium. Now that is thermal. Now what is thermodynamic equilibrium? The word equilibrium means what happens now, no more change. Okay, the moment it reaches equilibrium means there is no more change in the temperature or whatever quantities of the maybe tea also, maybe the air also outside. Nothing is happening once it reaches equilibrium. So the word equilibrium is basically no more further change will happen. What is this thermodynamic? Just now I told you what is a adiabatic wall. First, take a box which is surrounded by a, okay, this is also called as a system. You can also say it as an isolated system. Now what is happening? There is some substance inside. It will have all the macroscopic properties, that is the pressure, and it will have some volume. Because it is closed inside, definitely some pressure will be there on that. Volume means how much quantity is present, okay, or how much it is spread out to. Mass will be the actual matter, how much is present inside it. Then the temperature. So these are the macroscopic variables or the properties of that particular substance which is trapped inside. Whatever you had put it in, okay, at some point, maybe you had put it at 30 degree, and then pressure was at some other volume or something. All this, you keep it for 1 hour, suppose. Even after 1 hour, because this is purely in isolated system, it is not allowing anything to transfer from inside to outside. So what is happening? Basically, there is no change in the properties. Okay, so there is no change in the macroscopic variables. Why? Because it is not having anything to pass out to, because this is what adiabatic wall, or also called as an insulating wall. So no change means, I told you, it is at equilibrium. Even though the temperature here may be outside is 20 degrees Celsius. Okay, this and this temperature might be different, but the problem is this one also is not changing according to this one is also not changing according to this, because they are isolated. This one is independent of the surrounding and the surrounding is independent of what is there inside. So what is it? The basic concept, there is no change happening either in the outside surrounding or in the inside surrounding. So that's why it is called as, it is said to be at a thermodynamic equilibrium. Okay, what you can write it as, consider a gas inside a closed container, completely insulated from the surrounding. Its pressure, volume, mass, temperature, and maybe the composition of the gas does not change with time. Okay, so therefore the definition wise, a system is said to be in state of thermodynamic equilibrium if the macroscopic variables of the system do not change with time. So this is thermodynamic equilibrium. As long as there is no change in the mass, temperature, pressure, whatever the macroscopic properties, then it is said to be at equilibrium. And the next term is thermal equilibrium. First, I'll just explain. What they do is they conduct an experiment. You can put this way also. This whole thing, this blank, no, this is full adiabatic wall, means insulating wall. They try to put some substance A in this. They put some another different substance B in this. With different. This one has different this macroscopic variables. This one has different macroscopic. Means what? This one will have different pressure. Maybe PA now will represent. This one also will put different pressure, different volume. Now what is going to happen? Now this full thing is adiabatic wall. This one is going to have different one, this one. So there is no heat exchange. It will, even with after 1 hour if you check, this will remain the same. This will also remain the same. Okay, right now they are at in which state? Thermodynamic equilibrium. This one. Because they are basically nothing to do with the surrounding. They are in their own world. This one is in its own world. It has nothing to do with A has nothing to do with B, nor it has nothing to do with the surrounding environment because they are fully covered with adiabatic wall. Now what we do is we just remove this wall and we replace it by the other one, diathermic wall. Now what will happen? Now slowly, suppose this was at different temperature, this was at different. Now what is going to happen? They will start flowing between each other based on which is at a higher one. Okay, so energy will start getting transferred from higher to lower, whichever way it is. And then slowly with time, they will again come back to equilibrium. They will settle at a common point between both of them. Now obviously, their pressure also will change because it will try to find a middle point between balance between both the pressures, volume also, whatever pressure. So what is going to happen is this will have a different one, PA dash, PA dash, this will be PB dash, PB dash. And you know that now PA dash will be equals to PB dash. Here they won't be equal. PA won't be equal to this. And VA dash will be equals to VB dash. Because at thermal equilibrium, they will settle at the common same value. Okay, then this state where both pressures come to equal point, that is called as thermal equilibrium. So you draw this diagram, then I'll give you the explanation part. If you don't understand something, then please ask now. Okay, if you want to represent in terms of temperature also, if this is TA and this is TV, then temperature of A will be equals to temperature of B. We use capital T, no? This also. So as per the definition, two systems are said to be in thermal equilibrium with each other if they have the same temperature. And then no more changes will take place in the system. Two systems, A and B, are said to be in equilibrium if they have the same temperature. You can just write, consider two gases A and B in two different vessels. Let PA, VA be pressure and volume of gas A, and PB, VB be pressure and volume of gas B. So in the first case, what is happening? If case 1, first case, okay, as per the diagram, two vessels are separated by the adiabatic wall. Then pressure and volume of gas A and gas B are at thermodynamic equilibrium. Means they are in their own world. Case 2, adiabatic wall, or the two gases are now separated by diathermic wall. So now you can say, so now the pressure and volume of both gases will change. Will change to PA dash, VA dash, and PP dash, and VB. And will be now in equilibrium with each other. There will be no more flow of heat. Now once they settle to a common point, there will be no more flow of heat. Okay. Both systems A and B, you have to explain in your own words. Both systems A and B will attain equal temperature now. and are said to be in thermal equilibrium with each other. Okay, so this is called as thermal equilibrium. Whenever you bring any substance which is at a different temperature from the second one in contact, obviously there will be some flow of heat of energy till they come to a equal temperature, and then no more changes will take place, no more heat, and then it is called as thermal equilibrium. Next is called as the zeroth law of thermodynamics. First I'll just give you the law and then later explain. Zeroth law of the thermodynamics. It states that if two systems A and B are in thermal equilibrium with a third system C, then A and B must be in thermal equilibrium with each other. Just write this, I'll explain. Okay. What we do is, first of all, A and B. Consider this. And this fellow is C now. Imagine first we are putting all adiabatic only. Consider this whole thing is adiabatic wall. Now what is going to happen? This will have a different temperature. B is having a different temperature, suppose, and C is having a different temperature. Now, as long as there is adiabatic wall, means insulating wall, there will be, okay, even though it's not there like this, it's assumed to be insulated from all the sides. Huh? They were under their own, this what is that, thermodynamic equilibrium. No change will take place even after 1 or 10 hours. As long as this is insulated, this will remain as it is, the way you had put. Here also, this substance also will remain as it is. C also will not change its state as long as everything is adiabatic. Now what we do is, we just try to only remove the top one, not this. Okay, on the same diagram on the electron. So now I'll make this diathermic wall, and the rest, this is adiabatic. Now what is going to happen? There will be some exchange of heat, we don't know which side, and A and B are not in contact, huh? But what is happening? A is in contact with C, B is also contact with C. So some heat exchange will take place between B and C. Same way some heat exchange will take place between A and C. So as per the law of thermodynamics, after some time, now what will happen? Temperature of A should become equals to temperature of C. Okay, because you have removed this wall, now heat exchange will take place. They will try to settle to one temperature. Same way, B also will try to settle with C at the same temperature. Till then, exchange will keep on taking place. So when we actually check this one's temperature also, if T is equals to Tc and T is this, so it says that A and B also must be equal to each other. Why? Because what they do is, after this process, now how is this concluded? Now this something is happening. Now in the next step, okay, what they do, they remove this C. They just remove the C and then they keep only A and B among each other. Now imagine the C is removed. If they were at different temperatures, what would have happened? Some changes would have started taking place. But once they remove the C, after all that, they notice that there is no change taking place. No change means what? Definitely they are at equilibrium. And once they are at equilibrium, means you can already conclude that their temperatures must be equal. That's why they are not changing. Okay. So the three steps which are done is, everything is adiabatic. I'll just name it as A. Okay, then should not be any confusion. I'll just write adiabatic. Okay, this is step one. Then what they do, they make this diathermic. And then they make this fellow diathermic. Even if this is there, doesn't matter. Everything they make diathermic. But then they notice no change. And that's why they will conclude that A and B are also in thermal equilibrium. So you can just roughly draw this. First one, first thing is adiabatic. Second, they make only this one. So then the heat exchange will take place. Third one, they make this also diathermic. But till then, they are already in equilibrium. Okay, that's why there will be no change. We can conclude temperature of A must be equal to temperature of B. So what it says is zeroth law. It states that if the two systems A and B are in thermal equilibrium with the third system C, okay, then what must be this? A and B also must be in thermal equilibrium with each other. If A is in thermal equilibrium with C, B is in thermal equilibrium with C, then A and B also should be with each other. So a shortcut, if you want to say, if TA equals to TB, TB equals to TC, then TA must be equal to T. This is for the diagram. So I'll just explain in terms of this. These two experiments. Okay, first part. This part they have not explained in the textbook also, so we'll directly explain this first. So what is it? We can consider this as case 1, this as case 2. A and B are separated by adiabatic wall, and A and B are separated from C. We cannot are separated from C by a diathermic wall. It allows only the heat to flow, not the substance. Like considering, suppose if there was water, this water will not go in this, and water from here will not come, only the heat, okay, the pressure. So this is separated by a diathermic wall. Now what is going to happen? Heat exchange will take place exchange won't, don't say heat flow, you can say heat flow will take place between A and C, and also B and C. So what is going to happen? The moment this is diathermic, there will be some exchange of heat between A and C and between B and C. Hence A and C, I'm putting in the bracket, and B and C will reach at equilibrium separately, because A and B are not involving with each other because there was a adiabatic wall between A and B. Between them separately, they are coming in contact with, A is coming in contact with C, B is coming in contact with C. As of now, there is no contact between A and B. Now case 2, if the adiabatic wall is now removed, and replaced by diathermic wall, there will be no exchange of heat between A and B. Hence, you can say that A and B are already in thermal equilibrium.
Excuse me, miss.
Yes.
As this means that the pressure and volume of A and B will be same, right?
Yes, at some point at the equilibrium. In term now they are not given specifically in terms of that. What they will be telling is only in terms. Normally we don't write actually because we are dealing with only thermodynamics. So they explain only in terms of temperatures. So not needed actually to tell that pressure and all remains the same. Important is now the next sentence in terms of temperatures. Now what happens for the zeroth law? Zeroth law implies that if TA equals to TC and TB is equals to TC, then TA will be equals to TB. This is important. Okay, so this is about zeroth law. Next concept is internal energy. Now we previous chapters we had seen that total energy is normally taken as kinetic energy plus potential energy. Okay, any total energy of any system, suppose, then it is usually taken as kinetic plus potential. Kinetic will be definitely related to the motion or the movement. If any movement is taking place, there's a displacement, okay, then it is related to kinetic. Now this potential means either it is stored, okay, at a height, suppose. So I told you water tank at a height and all, it should be above the ground. Definitely there should be height. Then there are potential energy can be due to various forms. One is gravity, okay, due to gravitation. Why? As long as there's some force which is been implied, no? Now this force can be in the form of various forms. Like if you keep a box at a height, okay, what is happening? Your gravity is trying to pull it down. So basically it is under some force. Some kind of attraction is there from the earth, but it is trying to store it inside. So that is called as potential, which is given as mg. Then this could be like gravitational field, not exactly the word field or the force. Gravitational force, then it could be due to some you can say electrostatic force. Electrostatic means if you are supplying any conductor is there and some electricity is passed, it will always have electric field around any conductor. Any object placed under the electric field would be subjected to some force. You don't have to actually know in detail. Like there are various kinds of forces, electrostatic force, okay, due to some electricity. Then it could be due to some magnetic force. If you're keeping a magnet and trying to apply some force against this, because of that also whatever energy is then this object that would be considered as potential. Then you can also be something called as intermolecular, or that will come here. So some kind of force. Okay, so any object under some force would have some potential energy. Now we'll just modify this concept. Total energy might not necessarily be only this much. There's something called as always, which is actually very minute. But since we are doing the thermodynamics chapter, we have to consider it now in detail. So total energy is actually kinetic energy, potential energy plus internal energy. This is what of the body, suppose potential energy of the body. The internal energy will be of any substance, it is made out of molecules or atoms. Energy of the molecule or atom inside the object. Now consider it as a container. Okay, and there is something filled up inside. Some gas is there or whatever is there inside. Now this, suppose this container is moving and it is at some height, okay, from the ground, and it is moving this side. So obviously you know that it would have kinetic energy because it is moving. This is moving with velocity v. So there's a movement, okay. So it will have kinetic energy. It is at a height, so there's a gravity which is pulling it down. So it is under gravitational force also. So it is having potential energy plus these molecules are having its own internal energy. So basically, total energy would be this kinetic energy, potential plus the internal energy of the molecule of the whole system. Total energy of the whole system is all the three. So now we'll be studying in detail about this internal energy. Now what is going to happen? Same way how the box is moving. Now this molecule inside, we know that they are also free sometimes to move. Okay, not like too much space, but even at a minute level. So they also must be moving sometimes. They also must be having some attractional force between each other. Intermolecular forces they are called. Okay, they are, so every molecule inside also will have some kinetic energy as well as potential. Now this is of the whole body. This is different. Now what I'm talking is of each molecule. So each molecule is like one box you can consider. So that box is moving also, and then it is also under some force from another molecule. Okay, so same thing. Internal energy can also be written as sum of molecular kinetic energy. I'm mentioning the word molecular because it's of the molecules I'm talking about, not of the box. Plus molecular potential energy. Now consider this box is at rest. The box is not moving. Will the internal energy be zero? No. Even the box, this one, kinetic energy of the box might be zero, and suppose if it is at ground, doesn't matter. Okay, it is not under gravity, suppose, and potential energy of this fellow also might be zero of the box, but the molecules there is always, they are moving, okay, amongst each other. So that is there. Then if you have two molecules, it's assumed that always they will have some intermolecular attraction between them. So they are always under force amongst each other. Otherwise, what would happen? They will not be bounded, no? They would break the bonds and then it would split. But why are they tied? Even though they can move within some boundary, they are always tied to each other by the intermolecular force. So any force exerted, I told you, is related to potential energy. So even the outside system is at rest, internal system is always there. Molecular energy plus this will be internal energy. Total is molecular plus this. So in terms of words, want to give the internal energy of a system is the sum of molecular, kinetic and potential energy. Common word, molecular belongs to both. In the frame of reference. Don't have to buy hard this, just understand. Relative, this is actually important from here to here. Potential energy. Frame of reference relative to which the center of mass of system is at rest. Means even if the system is at rest, the whole mass of this, the outer system, still this will be kinetic plus potential energy. Even without any external influence, there no movement, but internal, there is always some movement amongst each other. So now these molecules, what they are moving, then they can be in various forms. So we'll talk about molecular kinetic energy. The molecular kinetic, it is because of a movement of molecules. So there are various forms, there are various ways this can move. First one is called as a linear motion. Linear, or they also say it as translatory motion, and just use it as linear motion. So in a straight line, this is, means it would move this side, or could move, either it will move to x-axis or it could move to y-axis, could move in a straight line. Second one is rotatory motion. Means what is happening, the molecule could go this side or the molecule could go upwards. Rotatory motion means the molecule is rotating among itself, it's spinning. Okay, the molecule is spinning among itself, so that is called as rotatory motion. You can say spinning. molecule along its axis. This is suppose its axis, so it is rotating. In the third case, one could be vibratory motion. What is going to happen is it's not moving in a straight line or upwards or direct at very high temperatures and all, no. So this works only mostly for high temperatures. This molecule will start vibrating, okay, at the same place only, but just to and fro, very small distance. So that also can be considered. There is some movement taking place, the vibratory motion. So it comes under kinetic energy. So that is just right there. There is no space. To and fro motion. To and fro motion of the molecule about their mean position. Mean position means they have a fixed position. Like there's a molecule, it can vibrate only among this distance. It will go, come back, go only within the certain distance. It will not go from here to here. So these are the three ways a molecule could move. Mostly at high temperatures and mostly in liquids and gases. Rotation is also at high temperature. So all this basically kinetic whatever motion will always end up like a heat. Okay, that we'll see in detail later. So this is about the kinetic energy could be kinetic could be due to these three motions. What about potential energy? Internal potential energy or molecular potential energy. You know that molecules exert mutual force of attraction on one another. Therefore, they possess this is called as intermolecular potential energy. I can write shortcut P. Okay. If volume remember if volume increases, more the volume no, of a gas, more will be the potential energy. If volume increases, intermolecular potential energy increases. Means basically it means what? Like if there are only two molecules, what is going to happen? Force of attraction will be less. If you are increasing the volume, obviously more molecules, so more intermolecular force. More the force, more will be the potential energy. So if the volume increases, more will be the intermolecular forces, and that's why more will be the potential energy. So potential is this intermolecular depends on the volume. Okay, so the two types I told you, one is kinetic, could be because of those three motions, and potential energy is because of the intermolecular attraction of force. Now we'll see what about ideal gas. Internal energy of ideal gas. What they say is for ideal gas, no, for ideal gas, there are no intermolecular forces because they are inert gases. Or the ideal gas means they will be having no force of attraction. For ideal gases, there is no intermolecular force of attraction. So if there is no force of attraction, therefore no intermolecular potential energy. If there is no force of attraction, there will be no potential energy. Therefore, internal potential energy of ideal gases is zero. So total internal, what will happen? Total is kinetic energy plus potential energy. So only it will be kinetic and potential energy will be zero. Therefore, I can say, therefore, internal energy of ideal gas is purely kinetic. Because potential energy is zero because for ideal gas there is no force of attraction. When there is no force, means no potential energy. Two modes of energy transfer. If you want to transfer energy, to any system, basically you want to transfer, you want to give some energy to a system, you can do it in two ways. The two modes are, one is by providing it heat or by doing some work on that system. By providing heat In work means by doing some mechanical work, you can say to the system, by doing some mechanical work on the system. So two ways we can give energy to any system. One is by providing heat to the system or by doing some mechanical work. The two ways is, this is fire, this is heat supplied, or another way is to do some mechanical work. Can be some pulley, some piston, some weight maybe, because there is some gas. Now this is my system or the substance, whatever. So I want to provide energy to the system. So one way is just heat it up. So heat energy will go here. So it will gain the heat. So that means it has gained the energy. The other way is by putting some force on it, mechanical some force. So this is a movable piston. Consider now this is a fixed mass of gas. This is a gas, okay? In a cylinder. This whole thing is a cylinder. Provided with a movable piston. Suppose I want to increase the internal energy. Now my aim is to increase the internal energy of the gas. Can be increased in two ways. First is heat method. Place cylinder over a hot body. Okay, this will be the hot body. So directly the heat will be supplied. What is going to happen? Energy or heat energy from hotter body will flow to the gas due to temperature difference. Hence, internal energy will increase. And the second one is work method. push the piston down. So what basically is done is, now this is the gas, no? So this, they try to put some weight. Okay, now this will try to put some pressure on the gas. So what is going to happen is, the more this space, the molecules will come closer to each other. So the more the closer, there will be more of attraction, plus there will be more movement of this. Okay, basically work is done. So work is also energy. Whenever some work, so this pushing the gas or expansion or compression of the gas is nothing but work. So obviously will be some movement of the molecules while either moving from here to here. The moment the molecules are moving means some work is happening. So kinetic energy plus potential energy will increase. So its internal energy is increased by adding weight. Therefore, work is done on the gas. It's either compressed or expanded, whichever way. Therefore, internal energy increase. So these are the two ways you can increase internal energy. So I told you both are energies. So only there's a fine difference between both of them. I'll just give you the difference. Then we'll stop. This is heat, work. Difference between heat and work. Mode of energy, transfer due to temperature difference. When how energy gets transferred, heat energy, heat will come into picture only when this flow of heat will take place only when there's a temperature difference. Here, work by mechanical means, such as moving the piston or by adding weights. You are doing some mechanical thing such as moving the piston or adding the weights to it. When heat is supplied, molecules move faster in all directions, or I can write weight shortcut form. Molecules move randomly in all directions. Energy transfer Okay, you can say here molecule, one particular direction. Basically what it is, see, when you provide heat, no, now this molecule will go and heat here, this energy might go from here to here based on how much is the difference. Okay, heat may go from any molecule in any direction or direction, but whenever you're pressing the piston, suppose you're compressing, what is happening, all the gases are getting compressed, they're moving in one particular direction. Molecules move in one particular direction. That's why energy transfer takes place in random motion. Yeah, energy transfer takes place in an organized motion. So this is the difference between heat and work. Just the sign conventions, small. Because next class I just directly start with first law, thermodynamics, sign convention. Heat absorbed. If you are absorbing heat, then it is considered positive. If heat is absorbed, heat given out, loss of heat, this is gain, then it is considered negative. I told you in the last class also, if you are losing heat, it is indicated by a negative sign. Work, work done by a system called positive, work done on a system called negative. Means if the system is the box, okay, you are carrying the box, so compared to box, it will be negative. Now if the box is coming and hitting you, okay, so it will be a negative work on you, and the box is doing something positive. Means if the system is doing that work, then it is positive. Someone else is doing something on that system. And the last one, internal energy. This is simple. Increase in internal energy, negative. Stop here. Let's take attendance. I don't know. Now exams are also over. Still not attending.